Alright, welcome to the start of Chapter 4. Today we'll be talking about local maxima and minima. So first I'm going to start us off with a little drawing. Alright, so we'll look at a graph of a function that looks something like this. Alright, where we have x and y, and this is our function f of x. So first I'm going to label these 2 points here. We have some sort of peak over here, and we have a valley down here. Alright, and I'm going to go ahead and give these their actual names. So this is a local maximum. Alright, and this is a local minimum. And these are the definitions we're going to start out with today. So, a function f has a local minimum at a point P if f of P is less than or equal to the values of f near, I'm putting near in quotes for a second, near this point P. Alright, because near is a little bit subjective, but let's go ahead and take a look at our drawing. So, our point in our valley, we said, was our local minimum. And we see that in this general area, we are at the lowest point, okay, in this general area. So that's kind of where we get for points near P, okay? And then a local maximum is similar. So F has a local max at a point P if f of P, that value, is not less, is greater than or equal to the values of f near P. So again, for our local maximum in our drawing, it occurred at the peak. And for these values that are kind of near P, we have the max of all of those. That's our local maximum, the very top of that peak. Alright, so how can we find these points without looking at a graph? Alright, well, what do both points have in common? The local max and the local min, what do they have in common while we're looking at this graph? Specifically, maybe think about their derivatives. Alright, they both have a zero derivative. Right? If we drew a tangent line at both the local max and the local min, the slope would be 0. And so we have a special name for these points. For any function, f, a point P, in the domain of the function, where the derivative evaluated at that point is equal to 0, or the derivative at that point is undefined. We'll come back to that in a moment. Undefined. Well, this is called a critical point. Okay? So either if the derivative is 0 or it's undefined. Both types of points are critical points. All right? And then our last definition, I know we're starting off with a lot, but this is a critical value. A critical value of f, of the function f, is the evaluation at the critical point. So f of p, where p is a critical point. So it's just the y value for all x's that give critical points. Okay? So I said we were going to come back to a derivative being undefined. Alright, so now we're going to talk about that for a second. So the derivative is undefined in the following cases. Now this is not going to be an exhaustive list of cases, okay, but the most typical ones that we might run into. So let's say we have a parabola, okay, but there's like a hole in it. Alright, so here's a hole. Let's say this is, I don't know, at x is equal to 2. So our derivative would be undefined there because, well, the function doesn't exist there. So how can we evaluate something that doesn't exist? Okay? So our derivative would be undefined just at 2. We could take the derivative at 1 or at 3, maybe even 2.5, but just not right at 2. Okay? Let's see. We could have something that looks like this. So the graph goes up here, and then it also comes down here, right? So we have a vertical asymptote. There we go. A vertical asymptote. Again, say that's x is equal to 2. Well, the function does not exist there either, so we can't take that derivative. Again, we could have something that looks like this, where it stops and then continues again up here. This is called a jump discontinuity. Alright, where it keeps going like this, and we cannot take the derivative at this jump point here. So if this is x is -1, our derivative would be undefined there. And lastly, we have probably the most typical we'll see is this sharp point. Alright? So the function in these last two, in the jump continuity and in the sharp point, the function exists there, right? It's defined at this filled in circle, okay? And it's also defined at the point in the sharp point. So that's not the reason we can't take the derivative there. The reason we can't take the derivative at these bottom two examples is because the derivative changes too quickly there, okay? When we're dealing with a smooth curve, all right, and we are gradually sloping, our derivative is changing gradually, okay? So we can handle something like that. Where we have this jump discontinuity and this sharp point, our derivative would change too quickly. So it's not possible for us to actually calculate this. All right, so that is why we are undefined at these points. All right, so now we're jumping into the first derivative test. Okay, we have 2 points to make here. So if the first derivative, f prime, changes from negative to positive at a point P, then the function f has a local minimum. Alright, so this would look like, let's see, if we have a negative derivative, then we know we are going down. And if we have a positive derivative, we know we are going up. So, at this point would be our local min. Here we have derivative is negative, here we have derivative is positive. And here, derivative is 0. Specifically at the local min, right? Okay. Also, if f prime changes the other way, so if it changes from positive to negative at a point P, then f has a local maximum. So we have a positive derivative, so we have an increasing function, then we change to a negative derivative, which is a decreasing function. So here we have our local max, where f prime is equal to 0. Here we have f prime less than 0, and f prime greater than 0. Okay. Now we have the second derivative test, which, if you've noticed something about our first one, concavity plays a role in this, doesn't it? Okay. So we can determine concavity from our second derivative. Remember that? So our second derivative test tells us that if the second derivative is greater than 0, I'm going to say specifically evaluated at this point P is greater than 0, then P is a local minimum. Alright, because if the second derivative is greater than 0, we are concave up, right? Concave up, which corresponds to the first point in our first derivative test. So, concave up. So here our second derivative is positive. So then, if our second derivative evaluated at P is negative, well then P is a local maximum. So a negative second derivative tells us we are concave down, which looks like this. A negative second derivative. Alright, and lastly, if our second derivative evaluated at P is equal to 0, then this test tells us nothing. So it's inconclusive when we have to figure it out from there and maybe try the first derivative test instead. Alright. Okay, we have one more little note to make, and then I promise we're jumping into our first example finally. Gotta give a little more room for this note. So, this is an important note here. Not every critical point is a local min or max. I'm going to say local extrema. Okay, or an extremum for singular. You might see this on your homework, okay? This is just a blanket term for minimum or maximum, okay? So not every critical point is a local extremum, so it might not be a min or max, okay? Here's an example. If we look at the function f of x is equal to x cubed, alright, If we want to find the critical points, we take the derivative. So f prime of x is 3x squared. And we would set that equal to 0 and solve for x. We're going to do a whole example about that in a second. Alright, but just know x is equal to 0 is a critical point. However, if we look at the graph, our graph of x cubed looks something like this, where this is x is equal to 0, okay? And if we look at our first derivative, on the left-hand side, we have a positive first derivative. And on the right-hand side, we also have a positive first derivative. So our derivative doesn't change either way. So this is neither a local max or min. X is equal to 0 is neither a local max or min. It's still a critical point, all right, but it's not any kind of extremum. All right? Now we are ready to jump into our first example. So part A, use the derivative to find all of the critical points. All right, so we have our function f of x is equal to x to the 5th minus 15x cubed. First, we need to take our derivative, f prime of x. I'm just going to go right for it, okay? Hopefully we've had enough practice with derivatives by now. Again, if you ever need more of the intermediate steps, please send me an email and I'll be happy to work through it with you. All right, but this derivative here is going to be 5x to the 4th minus 45x squared. All right, and this was just a few power rules, right? So then we determined that we need, in order to find our critical points, our derivative must be 0 and or undefined. In this case, we are not undefined anywhere because polynomials are defined everywhere, right? So we don't need to worry about being undefined. Instead, we should look at where the derivative is 0. So we're going to set equal to 0. So if we want the derivative to be 0, we just have to find where that happens. So 5x to the 4th minus 45x squared. All right, so we've now set this equal to 0, and now we're going to solve for x to find what values of x make this equation true. All right, so let's go ahead and factor. What can we pull out of here? Well, we have a common factor of 5 and a common factor of x squared. So we can pull out a 5x squared. In our first term, that will leave us just with an x squared. And in our second term, 5 times 9 is 45. So we need negative 9. And we pulled out the x squared. So negative 9 is all we need there. All right. Then we can go ahead and look at this x squared minus 9. You've probably heard this term before, but maybe not in a while. This is called a difference of squares. And why is that? Well, we have x squared, okay, so that's a square. And 9 is 3 squared, so that's also squared. And the difference is that we are subtracting it. That's the difference, okay? And so we can factor a difference of squares as x minus 3 and x plus 3. All right, if you go ahead and FOIL this out, you can check that that is true. So now we have 3 separate terms, right? This is one term, second term, third term. And we want to set each one of these equal to 0 because if any one of these is 0, then we're multiplying by 0. And if we multiply anything by 0, we get 0, so this whole statement would be true. So any one of these can be 0, and our statement would be true. That's why we need to set each one. So set each one equal to 0 separately. And instead of saying 1, I'm going to say term. Set each term equal to 0. So 5x squared is equal to 0, x minus 3 is equal to 0, and x plus 3 is equal to 0. So that's what I mean by setting each term equal to 0. And now we're going to solve all of these individually. So our first one here, we can divide by 5, but 0 divided by 5 is just 0. And then we have x squared is equal to 0. Well, square root both sides, again, 0. Square root of 0 is just 0. So we get x is equal to 0. Next one, we add 3 to both sides, get x is equal to 3. And then we subtract 3 from both sides and get x is equal to negative 3. So these are the critical points. Critical points. We don't know yet if any of them are minimums or maximums. Alright, but these are all critical points. Part B is going to ask us to determine if these are max or mins. Okay? So, and it asks us to use the second derivative test. So, we have our first derivative, which is 5x to the 4th minus 45x squared. Our second derivative test requires us to take the second derivative, right? So, the second derivative is going to give us 20x cubed minus 90x. And now, the way that we use our second derivative test is we need to evaluate at each of our critical points. So we need to evaluate the second derivative at each critical point. I don't know why I keep putting an H there. Critical point. There we go. So let's see. Let's go ahead and start out with x is equal to 0. So at x is equal to 0, we have f double prime of 0. Well, that's 20 times 0 cubed minus 90 times 0. Well, that's just equal to 0, isn't it? And our second derivative test said that when the second derivative is equal to 0, that tells us nothing, right? So we're going to need to do a little bit more investigating for x is equal to 0, but we'll come back to this in a moment. Let's go ahead and look at positive and negative 3. So when x is positive 3, we have the second derivative evaluated at 3. So we have 20 times 3 cubed minus 90 times 3, and we get 270. We don't really care about the number in this case, we just care if it's positive or negative, right? So in this case, this is positive. So a positive second derivative tells us that we have a local minimum, right? Because we are concave up. And if we look at x is equal to negative 3, then we have the second derivative evaluated at negative 3, gives us 20 times negative 3 cubed minus 90 times negative 3, which is negative 270. So again, it's just the sign that we are interested in, so this is negative, which tells us we have a local maximum because we are concave down. All right. So we've discovered that x is equal to 3 is a local min. X is equal to negative 3 gives us a local max. But we still need to figure out what x is equal to 0 gives us. All right, so let's go ahead and use the first derivative test to further evaluate the point x is equal to 0. So we have our first derivative, which is f of x is equal to 5x to the fourth minus 45x squared. All right. And the way that we use our first derivative is we need to test points on either side of the point we are interested. Test points on left and right of x is equal to 0. So we want to pick points that are going to make this relatively easy calculations, right? Why pick a difficult number? And x is equal to 0 gives us pretty quickly that we could use negative 1 and positive 1, right? Use x is negative 1 and x is equal to positive 1 to do these calculations. So we want to examine the first derivative at x is equal to negative 1. So this gives us 5 times negative 1 to the fourth minus 45 times negative 1 squared. All right. Whenever we have a negative raised to an even number, the negative is going to cancel itself out, right? So it's going to be squared out essentially. And for when we're raising it to the fourth, it's just squared out twice, right? So it's super positive if you can be super positive, right? And then multiplying by 1 doesn't change our value at all, so we really just have 5 minus 45, which gives us negative 40. Okay, so we have a negative derivative on the left-hand side. And let's go ahead and look at the right-hand side. So this is 5 times 1 to the fourth minus 45, 1 squared. And we are just going to end up with 5 minus 45 again, which is negative 40. So, on both sides of x is equal to 0, we have a negative derivative. This means that although our derivative went to 0 at the critical point, it didn't change and go positive. So it kept going down. All right? So this means that it is not a local max or a local min. So it is neither. So x is equal to, not 1, 0 is neither a local max or min. And we'll go ahead and take a quick look at what this graph looks like. And it's going to look something like this. So we come up, down, level out, down, and up again. All right, and I'm going to go ahead and label these points. So this is negative 3, this is positive 3. So remember at negative 3 we said we had a local max. And at positive 3 we said we had a local min. And at x is equal to 0 we said we had neither. So we see that yes, we had a horizontal tangent line there. Alright, but the graph just leveled off momentarily as it kept decreasing on both sides. Alright, so that's what that can look like when you find a critical point that is neither. All right, let's look at example 2. So the value of an investment at time t is given by s of t, and the rate of change of the investment is graphed below. All right, so, well, this is the graph here. Can I lift this up? Okay, I had to hand draw this graph, I apologize. But so here we go, this is our graph. So what are the critical points for s of t? So the first thing I'm going to make a note of is that we are looking at the graph of the derivative. Graph of the derivative. Okay, so we know that the critical point is where the derivative is equal to 0. So, if we were looking at the graph of the function, not the derivative, the original function, we would be looking for the horizontal tangent lines. However, we are given the graph of the derivative. So, this graph is equal to 0 whenever it touches the t-axis. Okay? So, we are 0 at t is equal to 1. We are 0 again at 4. And then we're 0 again at 6. So it's really important we are looking at what we are given on the graph, and that we are given the derivative and not the original function. All right? So the critical points are x is equal to 1, 4, and 6. Not x, I apologize. T is equal to 1, 4, and 6. All right. Part B asks us to identify each critical point as a local max, min, or neither. All right. So we know that when the first derivative changes sign, positive to negative or the other way around, or we have a local max or min. Remember, we are looking at the graph of the derivative, not the graph of the original function. Okay? So here, a positive derivative means we are above the t-axis, right? So on the left-hand side of our first point, on the left-hand side of 1, we are above the x-axis, so we are positive. To the right of 1, we are also above the t-axis. So we are positive on both sides of the first critical point. So the derivative is positive on both sides of x is equal to 1. So this point is neither a max or min. All right. Remember, positive means above or below the x-axis. It does not mean increasing or decreasing. Okay? When we are looking at the original function and want to know the derivative, that's when we look at the tangent lines, but we were given the graph of the derivative. All right, now let's look at at t is equal to 4. I keep doing that. There we go. At t is equal to 4. So on the left-hand side of 4, we are above the t-axis, so we are positive. And on the right-hand side of 4, we are below the t-axis, so we are negative. Okay? So the derivative changes from positive to negative at t is equal to 4, All right, so we have a local max. And finally, we will look at t is equal to 6. So on the left-hand side of 6, we are below the t-axis, so we are negative. And on the right-hand side of 6, we are above the t-axis, so we are positive. All right, the derivative changes from negative to positive at t is equal to 6, so we have a local minimum. Okay. Lastly, we are to explain the financial significance of each point. All right. So, at t is equal to 1, we have neither a max or min, but the derivative was equal to 0. All right, so it's one of those cases where our function levels off for a bit, but it doesn't change direction, if you will. So, at t is equal to 1, the investment, right, because this is the rate of change of the value of an investment, the investment momentarily stopped increasing. Right, because the derivative was positive before leveling off. So it momentarily stopped increasing, but then it started increasing soon after. Okay, so at t is equal to 4, well, we went from positive to negative. All right, so the value peaked. Right, that's where we had a local max, so we had a peak. All right, so the value peaked and then began to decline. And then at t is equal to 6, well, we went from negative to positive, so the value started increasing again. All right, and so that is the financial significance for each point. All right, so that wraps up section 4.1. Please remember to take the comprehension quiz, and I'll see you again in the next lecture.